Hi there, and welcome to this lesson on Further Pure Mathematics 1 from the Edexcel International A-Level. We're up to Chapter 8 and proofs. We're looking at proof by induction, and in particular, we're looking at divisibility proofs. Quick reminder of proof by induction. We begin by proving whatever statement we have, that it's true for n equals 1. We then assume that the statement is true for n equals k, and given that assumption, we try to prove that the statement is also true for n equals k plus 1. Once you've done that, to finish the question, you do have to write something close to the following to get full marks. We have shown that the statement is true for n equals 1. We have shown that if the statement is true for n equals k, then it is true for n equals k plus 1. Therefore, by mathematical induction, the statement is true for all values of n that are members of the positive integers. Okay, here's a divisibility example. I think I'll let you have a go yourselves first. So pause the video and then come back to me. Okay, we'll go through this together. Don't worry if you struggled a bit. It does have a very different feel from the proofs that we did in the first chapter. The beginning is the same. You look at n equals 1 and see how that works. Putting n equals 1 into the expression gives us this, which becomes 4 plus 6 minus 1, which equals 9. Is 9 divisible by 9? Yes, it is. Therefore, the statement is true for n equals 1. Step 2 is assuming it's true for n equals k, which just means we put k into this expression for n, which is what we've done there. Step 3, we're trying to prove n equals k plus 1 is true if n equals k is true. Now, for this question, that means we put n equals k plus 1 into there. That's what we're trying to prove, that that is divisible by 9. If this is true, which is for step 2, putting n equals k into there. We begin nearly always with the n equals k plus 1 term. That is what it is. Now, splitting that up, we can take out 4 from here, so you get 4 times 4 to the k. Multiplying out the brackets will give us that. Then we factorize. And I've taken out 4, and you get 4 times by this, and then you'll get minus 18k plus 9. There is nothing random about what I've chosen to go in the brackets. I have deliberately chosen the statement for n equals k to go in the brackets, because that will be useful to us later on. This here we can factorize into 9 times 2k minus 1. Well, 9 into 2k minus 1 is clearly divisible by 9. 4 plus 6k minus 1 is also divisible by 9. That's our assumption, which means that 4 times it is also divisible by 9. We're assuming that's the case. So if that's the case, and therefore, if that is so, then the whole of that expression is divisible by 9. The first bit is because of the assumption we're making, and the second bit just clearly is. Therefore, this statement for k plus 1 is divisible by 9, as long as the previous statement is. That's just a reminder of what we were trying to do and what we have just done. And then you write down exactly the same statement as you always do for these questions. Have a go at the second example. Pause the video, then come back. Okay, we'll have a look at this one. Step 1 is putting 1 into the expression. That gives us this, which simplifies to that, which is 25 plus 1, which is 26. Is 26 divisible by 13? Yes, it is. So it works for n equals 1. Step 2 is the fairly trivial step of saying this is what we're assuming, and you just substitute k into this expression. That is our assumption. What we're trying to prove is that n equals k plus 1 is true if n equals k is true. What does that mean in this question? Well, put n equals k plus 1 into the expression, and you will get that long, complicated thing. And what we're assuming is true is n equals k, and that is putting n equals k into the expression. We start off with a k plus 1 term, and we work with that. So multiplying out these brackets, you get that. Multiplying out these brackets, that simplifies to just 2k, and that simplifies to just k. Taking out the 5 squared from here gives us 5 squared times 5 to the 2k. Taking out 2 squared from here gives us that. Taking out 3 gives us that. You may ask, why have we done that? What we're trying to do is to get these terms exactly the same as the terms in UK. And we've got 5 to the 2k there, so we want that here. 2 to the 2k minus 2 there, we want that here. 3 to the power of k minus 1 there, we want that here. That is the reason we've broken that up in that way. 5 squared is 25, 2 squared is 4, nothing else has happened there. And then the 25 we're breaking up into 2 parts. 13 times by 5 to the 2k plus 12 times by 5 to the 2k. The reason why becomes clear on the next line. This first statement is going to be a multiple of 13, clearly. And what we've got here, which is why we chose those powers earlier on, is the statement for UK in brackets. So 12 times by the statement for UK. That's just a restatement of what we wrote there. The first thing is clearly divisible by 13, and the second thing is divisible by 13 if n equals k is true. Therefore, UK plus 1, all of that thing, is divisible by 13 as long as UK itself is divisible by 13. That is us finished. That is what we were trying to do, and that is what we have just done. And it's these next 3 lines that you do have to write down at the end of each question. Now, there's an alternative method for doing divisibility proofs. I say alternative. The truth is the method we've just been doing is probably the alternative method. It's the method I think I was taught at school when I did A-level, but looking at textbooks, it does not seem to be the standard method. What I'm about to show you now is, I think, the standard method for divisibility proofs. And I think that this method probably is slightly easier for most questions, but not necessarily all questions. Before we look at it, you just need to think about a little bit of logic. Consider 3 integers, a, b, and c. Now, if either a minus b or a plus b, both of these things will be possible in a minute, if either of these things is divisible by c, there are only 2 possibilities. Either both of those things, a and b, they're both divisible by c, or neither of them are divisible by c. But if that expression, a minus b, is divisible by c, or a plus b, it works the same way either way. Either both things are divisible by c, or neither of them are. Or in the language of induction, if UK plus 1 minus UK, or adding the 2 terms, either of those things, if either of those is divisible by c, there are only 2 possibilities. Either both of the things are divisible by c, or neither of the things are divisible by c, which leads to this alternative method, standard method, for divisibility proofs. We assume that UK is divisible by c in the normal way, and then we try to prove this. We try to prove that either UK plus 1 minus UK, or the addition of the 2 terms. So either the difference or the addition. Sometimes one leads to a quicker, easier result. Sometimes the other does. But one of those things is almost certainly what you'll be needing to look at. And we prove that the whole expression is divisible by c. Because if that's the case, well, we're assuming that UK is divisible by c. And from the logic we were just saying, that means that the other term must also be divisible by c. I hope that all makes sense to you. Okay, I'll let you have a go at working your way through what all of that means for the example we just did. But we'll do it again using this method. So proving that this is divisible by 13 by finding this sum and showing that that sum is divisible by 13. Pause the video, then come back. Okay. So step 1 is the friendly step, put n equals 1 in. We've already done that, so we will rush to the answer. You get 26, which is divisible by 13. Step 2, that just means put n equals k into this expression, and that is what you get. Okay, step 3 is where things change. We need to work out f of k plus 1. Well, that'll be this. So the black expression there is f of k. The blue expression is what you would get if you put k plus 1 in for n. Tidying that up, I think, is just like we did on the previous example. So this tidies to this. The black terms, nothing happens to. Now, all I've done now is just change the color coding a bit to make it slightly easier to see what we're about to do. So we have 5 to the power of 2k plus 2 to the power of 2k minus 2 times 3k plus 1. And then we break this up into 2 bits. So we get 5 squared times 5 to the 2k, because it's the same power as that. We get 2 squared times 2 to the power of 2k minus 2, because it's the same power as that. And we get 3 times by 3 to the power of k minus 1, because it's the same power as that. Very similar to what we did in the previous example. Now, having done that, we can collect terms. First of all, a little bit of simplification. 5 squared is 25, 2 squared times by the 3 gives us the 12 from there. Now, adding things together, we've got 1 lot of 2 to the k plus 25 lots of 5 to the power of 2k. We add those together and we'll get 26 lots of 5 to the 2k. And over here, we've got 1 lot of this expression plus 12 lots of exactly the same expression. That'll give us 13 lots of that expression. Now, immediately you can see both 26 and 13 are divisible by 13. So f of k plus 1 is divisible by 13, which means if f of k is divisible by 13, we can say straight away f of k plus 1 also must be divisible by 13. Now, there is a lot less working there. So whilst I've called this the alternative method, I think it is the quicker method and the better method for most questions. You'd finish things off just by saying the normal 3 statements. Never forget to do that. Okay, I think this is the last example, a little bit more confusing. Have a go at doing it. You'll notice this time, rather than adding the 2 terms together, getting their sum, we're looking at the difference of the 2 terms, f of k plus 1 minus f of k. Have a go, and then come back to me. Okay, we'll go through this quickly. First of all, put n equals 1 into the expression. That gives us this. That simplifies to that, which is 133. Is 133 divisible by 33? Yes, it is. Step 2, just substitute n equals k into the expression. Very little happening on that step. Step 3, okay, this time we're finding the difference. F of k plus 1 take away f of k. That is what you would get if you put k plus 1 into this expression, and in the blue here we have what you would get if you put k into the expression. Now, we've taken out 11 here. We'll have 11 times 11 to the power of k plus 1 plus 12 squared times 12 to the power of 2k minus 1. And I think these 2 terms on the end here are the same as they were before. And the reason for doing that is we've then got the powers that you have in the term for n equals k. We've got 11 of these, take away 1 of those, so that'll give us 10 of them. Here, we've got 12 squared, 144 of these, take away 1 of them, that'll give us 143 of that expression. Now, we've done nothing with that, but the 143 we split up into 2 bits. It feels a bit arbitrary, but it's not. We've split it up into 10 and 133. Both those numbers make sense. 133 because that's what we're checking divisibility by, so it's got to be a useful number to choose. 10 is useful because it's the same as the number here. That means we're going to be able to factorize in a minute. So that was the reason why we split 143 up in that way. The left-hand side can then factorize into this. The right-hand side we don't need to do anything with. And what we have here in the brackets is the expression for n equals k. So we've got 10 times by f of k. You'll notice we're using function language on this question. It really makes no difference. Don't worry about that. They do change the notation, but the method works in exactly the same way. So we've got 10 times by f of k plus 133 times by this term. Well, this term is clearly divisible by 133. And if f of k is divisible by 133, then so is 10 f of k. So therefore, f of k plus 1 minus f of k will also be divisible by 133, following the logic that we mentioned a little while back. Therefore, f of k plus 1 is divisible by 133. That's what we were trying to do. And then at the end of the question, these are the three statements that I never change and you need to write down. That gets us to the end of the lesson, page 134 and exercise 8b. Have a go. Thank you very much for listening and cheerio.